this thing called Lewis dot formulas are a help in as far as figuring out how to understand the way that atoms bond together covalently. Okay, so today we're going to be looking at using, yeah, I know, we'll see if it'll settle down here in a minute. If it doesn't, we'll just stop using it. So, using Lewis dot formulas to determine how covalent compounds are formed. And since covalent compounds are formed by sharing electrons, this is also looking at how atoms how atoms share electrons. Okay? Covalent. C-O-V-A-L-E-N-T. Because covalent refers to the valence level of electrons. Remember that term valence? That means the electrons that are in the highest primary energy level of an atom. So covalent means meaning between or shared between two valence levels. So we're sharing the electrons in the valence level between two atoms. That's what the term covalent means. Okay? The goal, if we can call it a goal, using the word goal kind of implies that an atom has will, and atoms don't think, so they don't have a will. But the goal for covalent bonding is the same as for ionic bonding. Okay. Each atom is more stable ionic bonding. Each atom is more stable when they have a full valence level. I think the correct term is actually a full valence, but we're going to use level because students misunderstand when I just say valence. So let's just review real quickly about ionic bonding and how that works, okay? In terms of how we use it anyway, okay? Remember, when we say a full valence level, we're talking about electrons. Full valence level of electrons. So let's put together, real simply here, sodium and chlorine. I'm going to start with the orbital notation. So sodium has full first level, a full second level, and one electron in its third primary energy level. So 3s, or this electron right here in the third primary level, is the valence electron, the only valence electron for sodium. And chlorine has a full first level. First level only has 2 electrons. A full second level. Second level has both an S and a P sublevel. and has 7 electrons in the third level. Full S sublevel and 5 electrons in P. Okay. So here's sodium in the first column. It's in the third row of the periodic table. That's where that third primary level comes from. And we just have 1 electron right there where sodium is located. That's why we only have 1 electron in 3s. And these first 2 columns represent the S sublevel region. In this same primary energy level 3, chlorine's over here. And it has a full S level, represented by sodium and magnesium, and it's got 1, 2, 3, 4, 5 different electrons in the third level P sublevel. Third level P sublevel. So it has a total of 7 electrons in the valence level. 3, the primary level 3 is the valence level for chlorine, and there's 7 electrons there. Now, for ionic bonding then, what happens is one atom gives up electrons and the other gains the electrons. That's the way we think about it in this class anyway. So that both of them have then, at that point, a full outer energy level. Sodium's new outer energy level will be not its original outer energy level. It's going to lose 1 electron, and by losing that electron, what remains is the outer energy level is 2, and it's full. So that's how sodium gets a full outer energy level. This electron goes over here to the 1 empty slot that chlorine has, and that's all that chlorine needed to have a full outer energy level. So its third primary energy level is now full. When sodium lost an electron, the electrons are negatively charged. It has 1 more proton than electrons. So the sodium now has an ion of sodium with a 1+ charge. Chlorine gained an electron. It has 1 more electron than protons. Electrons are negative, protons positive, so chlorine now has a negative charge. And that's the way we did it with orbital notation. You can see how all the electrons moving around, or where they are anyway, with orbital notation rather. Now, when we did electron dot notation for that, we showed sodium with just 1 valence electron. 1 dot. We showed chlorine with 1, 2, 3, 4, 5, 6, 7 valence electrons. This is before we put in an extra electron. Alright, so with Lewis dots, we're going to have 1, 2, 3, 4, 1 on each of the 4 sides, and pair up as needed. So I got 4, 5, 6, and 7. That's the Lewis dot formula, or the Lewis dot notation for chlorine, or electron dot notation for chlorine. Yeah. Over here, yeah, it's only missing 1, so it needs one electron. Mm-hmm. We're going to get to it. Right now we're reviewing ionic bonding. We're reviewing, this is review for ionic. Okay? Now, sodium lost the electron up here. When we use electron dot notation, then we move the electron out of sodium's Lewis dot formula. The result is that we're going to have a sodium that has no electrons. At least that's what it's going to look like, no electrons. In fact, it actually has a full valence level. We just don't show it with Lewis dots. With Lewis dots, once you lose that electron dot, it's gone. You don't put the 8 electrons around it because the new highest level has 8. We don't do that. We just simply show it as none. So we talked about Lewis dots as saying we either get rid of all the electrons or we have 8 and we're done. Okay, at least at the beginning level where we are now. Okay, so since sodium is going to lose an electron, and electrons are negative and protons are positive, it has 1 more proton than electrons. This sodium now has a positive charge. And since this chlorine gained an electron, the result is that we don't have 7 electrons, we have 8. so it's negative. And we just put a bracket around it to show that that charge applies to the whole monoatomic ion of chlorine. Okay? So that's the way we did things for ionic bonding. I want to briefly sort of run the clock back and remind you about the shape of an atom. Okay? No, they both have their difficulties and both have their simplicities. You get, it depends on how deep you get in them. Okay, some students find this a little harder. Sometimes students find it a little easier. All right, remember atoms. So now we're not in review anymore. Okay, that was the review part. We're now getting into discussing covalent bonding. Okay, atoms, remember, had a nucleus where the protons and neutrons are located, and it has an electron cloud. Okay? We said covalent bonding is the sharing of electrons. Okay? So when atoms share electrons, they're not two separate things. They actually overlap or join up their electron clouds. So instead of having two separate particles, we really kind of have one big particle with two nuclei. Kind of ends up like this. That's a what? Cleaver. Well, okay. Here's the point, though. Listen, here's the point. The point is sharing electrons means you're also sharing the electron cloud. Okay? Sharing electrons means you're also sharing a small portion of the electron cloud. Does that make sense? Okay. Now, we could use orbital notation to show how this sharing takes place, but it gets really complex. Alright? And we want to try to keep it as simple as we can. So Lewis dots makes this sharing process easier to demonstrate, easier to keep up with things. And all Lewis dots do, listen please, in 3 dimensions, in the real world, you've got these two electron clouds that are overlapping. We're only using Lewis dots to keep up with the number of electrons and figure out how many electrons are shared between one atom and another. It's not the actual shape of a molecule. Got that? Lewis dots don't show you the actual shape of a molecule. The actual shape of a molecule is much more like this. Now this is actually two-dimensional, but think of it as two balls with little kernels in the center where they sort of overlap. It's kind of like bubbles. You've blown bubbles before and had them kind of join together? Yeah. All right?
Oh, yeah, that's really cool.
Yeah. That's kind of how the electron clouds look like they're overlapping. Okay?